we were discussing Weierstrass theorem. So let us recall the statement once again. So Weierstrass theorem. Okay, suppose f is a continuous function on some interval ab. So let f be in C ab. Okay, we shall assume a less than b, and suppose some epsilon bigger than 0 is given, then there exists a polynomial p such that the distance between f and p is less than epsilon, okay, such that this d suffix infinity f and p. Let us recall what is this once again. That is nothing but supremum of mod fx where x belongs to ab. This is less than epsilon, okay. Or in short, you can approximate any continuous function uniformly by a polynomial. That is what the theorem says. And another way of saying the same thing is that given any continuous function, you can find a sequence of polynomials which converges to f uniformly, okay. And this is a very well known and celebrated theorem, and quite old also, and so there are it is used also in several places. And one more thing is that there are large number of proofs of this theorem available in the literature, okay. Yeah, in fact you will find different proofs in different books, okay. There is a one proof in Rudin, there is another in Siemens, then there is another interesting proof in a book by Limay, functional analysis. So what I am planning to discuss today is a proof as given in Siemens, okay. That is relatively simpler. Of course the proof given in Limay functional analysis is also good and quite interesting, so you should read it sometime, okay. Now the first step of the proof which we have done the other day, it is this, that is, first of all, without loss of generality we may assume that the interval is 0 to 1. Okay. This is something we have discussed already, so let us not bother about it once again, okay. The advantage of the proof which I am going to discuss, which is from the Siemens book, is that it is a sort of constructive proof. It means it tells you what exactly is the polynomial that approximates the given function, okay. And those polynomials are also very well known polynomials. Those are known as Bernstein polynomials. Bernstein is a name of Russian mathematician. Bernstein polynomials, okay. We can define those polynomials for any f in C01, and those are defined as follows. Suppose for each n you have one polynomial, okay. So suppose I call that polynomial as Bn, okay, Bnf, that will be a polynomial, okay. Bnf will be a polynomial. So we should know how it is defined. So Bnf at x, this is defined as sigma k going from 0 to n. It's something similar to or something depending on the binomial coefficients. So sigma k going from 0 to n, nck, that is n choose k, x to the power k multiplied by 1 minus x to the power n minus k, and multiplied by f at k by n, okay. This is for any x in 0 to 1, okay. So you can try to understand this. What is happening here is that you take the, see, suppose this is the interval 0 to 1. For any fixed n, you subdivide the interval into n subintervals, each of length 1 by n. So those endpoints will be 0, 1 by n, 2 by n, etc. Only k by n. So you evaluate, suppose this is k by n, you evaluate f at k by n and multiply it by this x to the power k, etc., etc. You will get some value, and do it for each point and take the sum, okay. Now it is obvious that this is a polynomial because x to the power k into 1 minus x to the power n minus k, that is a polynomial, and you are taking combinations of such terms. So this is a polynomial, it is a polynomial of degree n, okay, degree n. Alright. Now before proceeding further, we will need some properties of these, not exactly of these polynomials, one special case of these polynomials. Okay. So suppose I take f as a constant function 1, okay. Suppose I take f as a constant, that is, so what will it be? It will be Bn 1 of x, okay, that is you take fx as a constant function 1. Okay. Then this will be sigma k going from 0 to 1 n nc k x to the power k 1 minus x to the power n minus k, and this f at k by n will be 1, okay, f at, because we are taking f as a constant function 1. So this is nothing but the binomial expansion of this x plus 1 minus x, right. This is nothing but x plus 1 minus x whole thing raised to n, okay, right. Okay, so this is nothing but 1, okay. And similarly for your own interest, if you can try to calculate what is, suppose you take fx equal to x, fx equal to x square, what is the corresponding Bernstein polynomial, you can try to calculate on your own, okay. For things like x, x square, x cube, etc., you need to have some simplification. It will not be as simple as this, but not very difficult also, okay. What we plan to do further is that we want to get some, this is one thing which we shall be using in the proof, that is this is equal to 1, but there is one more identity which we need, and that is obtained by differentiating this with respect to x, okay, that is differentiate with respect to x. So what we will get is, okay, let me write it here, okay, sigma k going from 0 to n, this nck is anyway a number, so I will just put it outside, and then you differentiate, so it will be k x to the power k minus 1 into 1 minus x to the power n minus k, then plus x to the power k into, it will be n minus k into 1 minus x to the power n minus k minus 1, and because of this minus x you will have a minus sign here, okay, and this is equal to 0, okay, alright. Now let us simplify, because in both of these terms what you have is, here you have x to the power k minus 1 into 1 minus x to the power n minus k minus 1, that will be common in both of these terms, right, okay. So we will take that, so this is same as saying that sigma k going from 0 to n nck, I will write it here as x to the power k minus 1 into 1 minus x to the power n minus k minus 1, and what remains here k, from here you will get k into 1 minus x, okay, because 1 minus x to the power n minus k minus 1 is a common factor, k into 1 minus x, and from here minus n minus k into x, that is equal to 0. Okay, all right. So simplify this. So this is k minus kx minus nx plus kx. So kx will cancel. So this term will simplify to, I will simply write it here, k minus nx. Okay. Is it okay? K by, so this will simplify to k minus nx. Okay. So what I want to do further, because we want to have obtained one identity by differentiating this once more, but before doing that I will simplify one more thing so that it looks more like this original polynomial. To do that I will multiply this by x into 1 minus x. Okay. So multiply by x into 1 minus x, x into 1 minus x, so that power of these two will increase. Okay. So this is, so by that we will get sigma k going from 0 to n nck x to the power k into 1 minus x to the power n minus k, and then multiplied by k minus nx, and that is equal to 0. Okay, we agree with this? Okay. Now differentiate this once again with respect to x. Okay, differentiate this once again with respect to x. Okay, and since in the earlier step we have differentiate this term x to the power k into 1 minus x to the power n minus k, and its derivative we have already met. So we can treat this as one term and this as another term in the product formula. Okay, right? Okay, so while doing that we will do this. Okay, sigma k going from 0 to n, this n c k remain as it is. So first I will write a derivative of this. So what is that? It is x to the power k minus 1 into 1 minus x to the power n minus k minus 1 multiplied by k minus nx, and this has to be multiplied by k minus nx. Okay, so this is k minus nx square. Okay, k minus nx square, then plus this term as it is, x to the power k 1 minus x to the power n minus k, and then derivative of this, that is minus n. Okay, is it okay? Okay, all right. So okay, so what I will do now is that this term, okay, this is minus and here I will make this plus, so minus, and this term I will take to the other side. Okay, this term I will take to the other side. So what we will get is, that is sigma. Okay, I think I will continue here. Sigma k going from 0 to n, n c k x to the power k minus 1 into 1 minus x to the power n minus k minus 1 into k minus nx square into k minus nx square, that is equal to n into, see, n into sigma k going from 0 to 1 n c k x to the power k into 1 minus x to the power n minus k, right? Do you agree? Okay, but we know that this is 1, right? That is what we have. So okay, so this is same as n, this is same as n. Okay, right? Okay, and then I do the same thing once again whatever I did in the previous step, multiply the whole thing by x into 1 minus x. Okay, multiply the whole thing by x into 1 minus x. So okay, again multiply by x into 1 minus x. So what we will get is, oh, this we wanted anyway, sigma k going from 0 to n n c k x to the power k 1 minus x to the power n minus k, because we are multiplying by 1 minus x also, multiplied by k minus nx square, that will be same as n x into 1 minus x. Okay, all right, and okay, I will do the simplification here itself. I will divide the whole thing by n square. I will divide the whole thing by n square. So okay, so here itself I will say multiply by x into 1 minus x by n square, x into 1 minus x by n square. So what will have, right hand side will be x into 1 minus, instead of this it will be x into 1 minus x by n. Okay, x into 1 minus x by n, and here it will be k by n minus x, correct? So that is, we are dividing this by n square, so k minus nx by n whole square. Okay, right? Okay. So this will simply I will rewrite this as this term as x minus k by n whole square, that is equal to x into 1 minus x by n, right. Okay, this is an identity which we shall require. Okay, so this one and the first one which we started with, okay, I think this in between things I will remove now. Okay, what was the first one? Sigma k going from 0 to 1 nck x to the power k 1 minus x to the power n minus k, that is equal to 1. Okay, in fact this is, we started with this differentiating this and all that. Okay, so this is 1 and this is 2. Okay, all right. Now we look at, okay, let me remind it, what was our definition of BNF of f of x? It was sigma k going from 0 to n nck x to the power k into 1 minus x to the power n minus k into f of k by n, f of k by n. Okay, right. So suppose I want to consider this fx, our idea is to show that for large n, mod fx minus bnx is less than epsilon. Okay, right, for large values this is the required polynomial. Okay, this is the required polynomial for large values of n. Okay, that is what we want to show. Okay, now to do that we will have to estimate the difference between fx minus this polynomial. Okay, fx minus this polynomial. So to do that we will again do as follows, we will write fx minus Pn f of x. Bn f of x is here. Okay, Bn of x is here. Okay, that is what we have seen already. Okay, for fx I will use this identity. Okay, I will multiply both sides of this identity by fx. Okay, I will multiply both sides of this identity by fx. So what will happen? It will be so it will be fx into this is equal to fx, and I will take that fx inside this. Okay, I will take that fx inside this. What is the advantage? All these terms are common, and what we will get is fx minus f of k by n. Okay, so I will write it like this. This is same as sigma k going from 0 to n nck x to the power k 1 minus x to the power n minus k and multiplied by fx minus f of k by n. Okay, do you agree with this? No? Okay, so here we have already used this identity and this identity. Okay, we want the difference between the absolute values. Okay, we want difference between the absolute values, so I take the absolute values here. I will take the absolute values here. So this equality will be replaced by less than or equal to, this nck is anywhere non-negative. Similarly x is between 0 and 1, remember. Okay, everything is happening between the intervals. So x to the power k 1 minus x to the power n minus k, all those are non-negative terms. Okay, so that will not be affected by taking absolute value. This will become mod fx minus f k by n. Okay, okay. Now till now whatever we have done could have been done for any function. We have not used anywhere the fact that f is continuous till now. Okay, these are just algebraic manipulations. Okay, up to this point I could have done for any function. Okay, now we shall use the fact that f is continuous. Okay, to show that this difference can be made less than epsilon, we have to show that each this sum can be made less than epsilon. So first we shall use the continuity, and we also need to use this identity. Okay, let us see how to proceed. Okay, again since f is continuous in 0 to 1, you know that every continuous function on a compact set is uniformly continuous. So we can find some delta. So we can say that since f is uniformly continuous, on 0 to 1, we can say that there exists delta bigger than 0 such that whenever mod x minus y is less than delta, this implies mod fx minus fy is less than epsilon. Okay, all right. Now, you look at this sum here. Okay, here you have a term of the form fx minus fy. Okay, fx minus fk by n. Okay, now remember x is a fixed point. Okay, x is a point which in the interval. What are these k by n's? That will depend on what is k. Okay, this is 0, 1 by n, etc. There will be k by n here. Okay, okay. X may be somewhere here. Okay, so let us say this is k by n for various values, and let us say x is some such point here. Okay, so now given any delta, there may be some case for which mod x minus k by n is less than delta, and there may be some case for which this is false. Okay, fine. But at least for those cases for which mod x minus k by n is less than delta, we can say that mod fx minus fk by n is less than, let me make it epsilon by 2. Okay, the remaining sum also we shall make epsilon by 2. So first what I can say is that I can say that I will split this sum into 2. Okay, I shall split this sum into 2. So the first term is, let me for the sake of convenience, let me simply write it here. Suppose I call this as sigma prime plus sigma double prime. Okay, sigma prime plus sigma double. So what is sigma prime? Sigma prime is I take only those indices k for which mod x minus k by n is less than delta. Okay, that is I'll for okay. Let us write it. Sigma prime is this. Sigma prime is sigma k going from 0 to n and mod x minus k by n less than delta. That is, take only those delta for which mod x minus k by n is less than delta. Okay, whatever is this nck x to the power k 1 minus x to the power n minus k and multiplied by mod fx minus f of k by n. Okay, all right. Now we know that this part is less than epsilon by 2. Okay, this part is less than epsilon by 2. So for all such case, this is less than, so that will come outside the summation sign. Okay, so this is, so we can say this is less than epsilon by 2 into this okay, sigma whatever all this, sorry, sigma etc. Okay, it is sigma k going not k going from 0 to 20, it is sigma over some case, but the terms involved are the same as this, right. Remember, once I take this epsilon by 2 outside, what remains inside is, okay, let me just write once again here. Okay, nck into 1 minus x to the power k into 1 minus x to the power n minus k. Okay, only thing is it is not sum over all case, but sum over some case. Okay, sum over some case. Is it clear that this must be less than or equal to this, right? Because this is the sum over all case going from 0 to n, and we have taken just some terms from there. Okay, so that should be less than or equal to 1. So this must be less than epsilon by 2. Okay, at least as far as this part it is straightforward. Okay. Now our idea is to show that this remaining part sigma double prime, that is also less than epsilon by 2, but here it may not be for all n, but for large values of n. Okay, that is what we shall show. Okay, what is sigma double prime? Sigma double prime, that is nothing but sigma, okay, let me write here. Okay, sigma double prime, that is equal to sigma k going from 0 to n, and with what case, mod x minus k by n is bigger than or equal to delta, with that property, mod x minus k by n bigger than or equal to delta. Okay, all right. Okay, and okay, what are the terms here? nck x to the power k 1 minus x to the power n minus k into mod fx minus f at k by n. okay. 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 Now we as such we can't say that mod fx minus f k by n is less than epsilon by 2 in for this case, okay, but we can say something, okay. Since f is continuous function on the compact set, it is bounded, okay, it is bounded. So we can always find some number m such that mod fx is less than or equal to m for all, okay. We can say that on AB also we can say that there exists m bigger than 0 such that mod fx less than or equal to m for all x in AB. Okay. So what we can say is that this is less than or equal to, this is less than or equal to sigma k going from 0 to n mod x minus k by n bigger than delta into all this n c k less than or equal to 2m into this 2m into sigma k going from 0 to n n c k x to the power k into 1 minus x to the power n minus k, okay, right. And again we can say that since x to the power k 1 minus x to, again whatever remains here, that is less than or equal to this, so this is less than or equal to 2m, okay, this is less than or equal to 2m, okay. But of course that is something we could have got even otherwise. What we also what we will also use here is the following, okay. We have not yet used this identity, okay, we have not yet used this identity. The way in which we plan to use is this, because for those case for which mod x minus k by n is bigger than or equal to delta, this term x minus k by n square, that will be bigger than or equal to delta, okay, that will be bigger than or equal to delta. So since sigma primes involves those terms x to the power k into fx minus f of k by n etc., we shall use this fact here that okay, let me continue here. This is from here what follows is the following, that is x into 1 minus x is this sigma k going from 0 to n n c k x to the power k 1 minus x to the power n minus k into x minus k by n square, okay. That is something that is this divided by n, x into 1 minus x divided by n, okay. What we can say is that this is bigger than or equal to sigma k going from 0 to n, but instead of taking sum over all k, suppose I take sum over only those k for which mod x minus k by n is bigger than or equal to delta, okay, right. n c k x to the power k 1 minus x to the power n minus k into x minus k by n whole square. Is this part clear? Okay. All that we are doing is we are taking only some of these terms here, okay, and all the terms are positive. So if we drop some of these terms, whatever remains should be less than or equal to the original sum, okay, okay. But what we know is that for these cases mod x minus k by n is bigger than or equal to delta, okay, mod x minus k by n is bigger than or equal to delta. okay. So this term x minus k by n whole square, that will be bigger than or equal to delta square, okay, that will be bigger than or equal to delta square. So we can say that this is bigger than or equal to delta square into sigma k going from 0 to n, nck x to the power k 1 minus x to the power n minus k, okay, not k going from 0, it k go from 0 to n, mod x minus k by n bigger than or equal to delta, right. And what we will now, you compare what expression we have got here with this, okay, the expression that we have got here with this, okay. Here you have the same 2m into nck x to the power k 1 minus x to the power k mod x minus k by n, okay. So what we have got here is that this, see here we have got that this expression is bigger than or equal to delta square into this, and this this expression which we have here is same as this last, not forget about it, this is same as this expression that we have here, okay. This is, okay, what is the inequality there, we can, okay, for the time being I will write it as this is bigger than or equal to sigma prime by 2m. Do you agree with this? Sorry, sigma double prime by 2m, okay, forget about this part, okay, this is something that we have not used, okay. Okay. So what we have is this expression sigma k going from, that is sum over these k's is bigger than or equal to sigma prime by 2m, okay, sorry, sigma double prime by 2m, okay. Is that clear whatever we have done till this, okay, yes, yes, yes,
upper inequality.
Delta square into
what is the doubt? Okay, this delta square, that is delta square sigma double prime by 2, okay, alright. Now we will just take this whatever we have got, we want to write sigma double prime less than or equal to something, that is our objective, okay. So what have we got, sigma double prime less than or equal to x into 1 minus x by n, okay, into 2m delta square, okay. Do you agree with this, okay. Of course you can check all these calculations once again, I mean those are fairly simple, okay, that is after you do. These are just adjusting some terms in the sum, okay, alright. Now again remember the whole thing is happening in the interval 0 to 1, 0 less than or equal to x less than or equal to 1, okay, right. Do you agree that in this interval x into 1 minus x will be less than or equal to 1 by 4 in the interval 0 to 1, that is for 0 less than or equal to x less than or equal to 1, this will imply that x into 1 minus x is less than or equal to 1 by 4 for all x, okay. It is a elementary maximum problem, okay. So okay, this I can remove now. So using this what we will get, this is less than or equal to okay 2m by 4 n delta, that is this is less than or equal to 1 by 4, already you have 2m n delta square, or that is same as m by 2 n delta square, okay, okay. Now is it clear that by choosing n large enough, this can be, because this m and delta square are fixed, m2 delta square are fixed, okay. So by choosing n large enough, this can be made less than epsilon by 2, okay, this can be made. So we can say that this is can be made less than epsilon by 2 for large n, okay. So again coming back to this we wanted to look at this difference, okay. This difference is less than or equal to this two part sum, this is sigma prime and sigma double prime. Sigma prime is less than epsilon by 2, that is what we have shown, okay. And remember this is for every x, okay. whatever estimates we have done, we may have started with some particular x, okay, but ultimately, for example, ultimately we have removed the dependence on x, okay, we have removed the dependence on x, because for example if you look at here, this up to this x was fixed, but after you come to this spot, this is less than epsilon by 2 for every x, okay, right. Similarly, up to this there was a dependence on x, okay, up to this, but after this we say that whatever be the x, x into 1 minus x is less than or equal to 1 by 4. So this is less than, so that what I wanted to say is that this n does not depend on x, okay, because here there is no x, here there is no x. So this inequality is, that is, this will be less than epsilon by 2 plus epsilon by 2, or which is equal to epsilon, that is mod fx minus bnf of x is less than epsilon for large n, and for that delta that is independent of x, okay. In other words, okay, I removed the statement, the difference between, that is, if you take the supremum of this for x in 0 to 1, that supremum is less than epsilon, okay, right. Okay. Okay. Now I have already mentioned that one of the ways of using Weierstrass theorem is that you can show that this CAB is separable, okay. This is something we have discussed already, okay. And let us say, what does this Weierstrass theorem say? If you look back once again, if I look at this space, suppose I look at these polynomials, let us say 1 x, x square, etc., etc., okay. If I look at these polynomials, these are all polynomials, right, and suppose I look at the span of this 1 x, x square, etc., suppose this is nothing but the set of all polynomials, right, okay, linear span of these functions 1 x, x square, etc., any element in the linear span will be a polynomial, okay, and every polynomial is in the linear span. So is this is a simple way of stating Weierstrass theorem, okay, that is P is dense in CAB, or that is I am saying that P closure is C01, okay. Now there are, as I said, there are several generalizations of Weierstrass theorems, okay. One generalization is to replace this set AB by any compact metric space, or more generally a compact, what is called compact Hausdorff space, okay, topological space, okay. And those are that theorem was also very famous theorem, it is known as Stone-Weierstrass theorem, okay, Stone-Weierstrass theorem. Where it says that suppose you take X as any compact metric space, then what are the subsets which are dense in Cx, okay, that is theorem which gives characterizations of those sets, okay. But we shall not go into the discussion of that, because that will take us too much away from the things that we are discussing here. But there is one more interesting thing that one can ask, is that whether all these functions are essential, okay, whether we can drop some of these functions and still the span of the remaining things will be dense, and which can be dropped, okay. And in that direction there is one very interesting thing, and that is the following, okay. Suppose instead of this set P, suppose we take some other set, okay. Suppose you take this set 1 x to the power n1, x to the power n2, etc., okay, where n1 is, where n1, n2, etc., there are some natural number, n1 less than n2 less than n3, etc. Suppose you pick up some such numbers, okay, and call this and suppose you take the span of this and call it this as q, okay. And suppose we ask a question, okay, when is this dense in C01, let us say, okay, when is this, or for what values of n1, n2, n3 this is dense in C01. The answer is very interesting and totally unexpected, okay, and totally unexpected in the sense from whatever we know at this level, okay. The answer is the following, okay? It is q, that is q bar, q is this, that is q bar is equal to C01 if and only if and only if you take this series sigma 1 by nk, take the series sigma 1 by nk, this is a divergent series, okay, okay, sigma 1 by nk is divergent. Okay, sigma 1 by nk is divergent. Okay, this is also a very famous theorem known as Mund's theorem. Okay, can you see that Weierstrass theorem satisfies this condition? Okay, because if you take all of, if n1 is 1, n2 is 2, etc., this will be sigma 1 by n. Okay, that is a divergent series. Okay, that is a divergent series. So the question is which n1, n2, n3 you can select. You can select only those if they form, if sigma 1 by nk forms a divergent series. Okay, that is why it apparently it is totally unrelated things, and so that is why somewhat unexpected in the beginning. Okay, all right. Now coming to the discussion back with the uniform convergence, see what we have already seen is that if you take any sequence of functions and if it is uniformly convergent, then it is pointwise convergent. Okay, and we have seen that the converse is false, and we have seen some special cases where the converse may be true, for example Denis theorem. Okay, now there is one more theorem of a similar type which we would like to see, and that is the, here we ask the question, suppose, okay, suppose we do not bother so much about the uniform convergence of the given sequence, does there exist a uniformly convergent subsequence? Okay, suppose even if the original sequence does not converge, at least does there exist subsequence which converges uniformly? Okay, now so there is a theorem which answers this question. Okay, and that is also very famous theorem, and that is called Arzela-Ascoli theorem. Okay, Arzela-Ascoli theorem. Arzela and Ascoli both were Italian mathematicians. Okay, now to again discuss this theorem, let us discuss a few preliminary things. Okay, you would have already discussed the various properties of metric spaces, and in particular compact metric spaces. Okay, and there are various equivalent characterizations of compact metric spaces. Okay, and just now I mentioned about the convergence of a subsequence. You know that there is a characterization of compactness also in terms of using subsequence, and what is that? We say that a space is compact, metric space is compact if and only if it is sequentially compact. Okay, it is, that is every sequence has a convergent subsequence, and it is also equivalent to saying that it is complete and totally bounded. In fact, this is something that we should remember always, that is, suppose we take X is a metric space. Okay, you may have studied this, but it is useful to recall this. Okay, then the following statements are equivalent. Okay, the following are equivalent. First is that X is compact. Okay, 2, X is complete and totally bounded. X is complete and totally bounded. And 3, X is sequentially compact. Okay, I simply write it, X is sequentially compact. X is sequentially compact. Okay, and and these are the characterizations which are useful to decide which sets are compacts, which sets are compact in the well-known metric spaces. Okay, so suppose we take the, let us say, the usual spaces Rn, etc. Okay, then you know that there is another famous theorem that known as Honey-Borel theorem, which says that a set is compact if and only if it is closed and bounded. Okay, it is closed and bounded. Okay, but you also know that this is not true in general. Okay, it is true only in R, R2, Rn, etc. Okay, it is true only, for example, in other metric spaces you can find the space sets which are closed and bounded but not compact. Okay, not compact. Okay, in fact it can be shown that this happens only in finite dimensional spaces. Okay, that is, if you take a norm linear space, that is vector space on which a norm is defined and which gives a metric, then every closed and bounded set is compact if and only if the space is finite dimensional. Okay. This is a very well known theorem, but that you will learn in functional analysis course. Okay. It is that requires some techniques in functional analysis, but anyway it raises one obvious question, that suppose you take an arbitrary infinite dimensional space. Okay. For example, the space which we are considering here, let us say that E is a compact metric space, and consider C of E. Okay. Then suppose I want to know what are the compact subsets of C of E. Okay. This is an infinite dimensional space. Okay. Since it is an infinite dimensional space, you can obviously find the sets which are closed and bounded but not compact. So the question that we are asking is the following: in addition to being, remember, a compact set is always closed and bounded. Okay. Compact set is always closed and bounded, only thing is converse may not be true, and for the converse to be true, it is just bounded is not enough, what we require is totally bounded. Okay. And in case of, and that is where the difference, in finite dimensional spaces boundedness and total boundedness are the same. Okay. But these are different in infinite dimensional spaces. Okay. So what are the properties of or what are the sets which are in addition to being closed and bounded, what gives the compactness? That is the question that we will ask, and that is the question which this theorem answers in this particular space CE. Okay. Suppose you take the set of all continuous functions on a metric space. Okay. And what is the answer? Okay. Let us say, what is the question? Suppose let us take this set, a non-empty set A in. A is contained in C. Of course, let us take non-empty. Okay. Non-empty subset, and suppose A is closed and bounded. Okay. Suppose A is closed and bounded. Okay. Then the question is, what additional conditions are required to make A compact? Okay. What additional conditions are required to make A compact? Okay. And that is the question that this Arzelà-Ascoli theorem answers, and there is a property which makes this compact, and that is the property which is called equicontinuity. Okay. Equicontinuity. So the theorem will ultimately say that A is compact if and only if A is equicontinuous. Okay. A is compact if and only if A is equicontinuous. Now to understand that, we will have to know what is meant by saying that A is equicontinuous. Okay. What is meant by saying that A is equicontinuous? So we shall just make this get this definition today, and the details we shall do in the tomorrow's class. Okay. So remember, this A is a subset of C of E. Okay. So if you take any f in A, then that is a continuous function in C of E. Okay. And since it is a compact metric space, it is also uniformly continuous. Okay. So suppose you are given epsilon bigger than 0, then there exists delta bigger than 0 such that distance between x and y less than delta, this should imply mod fx minus fy less than epsilon. Okay. Right. Okay. Mod fx minus fy less than, that is whenever distance between x and y is less than delta, that is the meaning of saying that f is continuous, and of course in this case continuous is same as. So given epsilon, you can find a delta. We already know that this delta will not depend on what is x because it is uniformly continuous. Okay. But it may depend on what is f. A is a family of functions. Okay. So given an epsilon, for different f's there may be different delta. Okay. For different f there may be different delta. Okay. But suppose you can find one delta which works for all f. Okay. Then that family of functions is called equicontinuous family of functions. Okay. Right. Okay. So we will say that A is, okay, let me say A is said to be equicontinuous family of functions if for every epsilon bigger than 0 there exists delta bigger than 0 such that distance between x y less than delta implies mod fx minus fy less than epsilon for every f in A. for every f in A, okay. So when we talk of equicontinuity, we are talking about the family of functions, okay, and in particular it can be a sequence of functions also, okay, right. In particular it can be a sequence of functions also, but it can be any family of functions. So equicontinuity is a property that a family of functions may or may not have, okay, alright, okay. We will discuss these things more in tomorrow.